To understand network architecture, we have to bypass the software entirely. If we strip away the top 6 layers of the OSI model, we isolate the foundation, layer 1, the physical layer. Every digital packet requires a physical bridge to cross a spatial void. The ones and zeros must be converted into a measurable phenomenon, a voltage wave on copper, a photon pulse in glass, or an electromagnetic wave. This creates the primary dichotomy in all of network design. We must either force that signal through physically constrained pathways, known as guided media, or broadcast it freely through the air as unguided media. This radar chart shows that choosing a medium is a strict mathematical compromise. Every engineering decision balances exactly 5 variables: speed, cost, distance, security, and noise resistance. We are going to analyze the 7 dominant physical mediums used in modern networking and plot them directly against this optimization matrix. At this layer, network design is about engineering strict environmental controls and spectrum strategies to guarantee that a fragile signal survives its journey. Guided media is an exercise in isolating a signal from a chaotic external environment. The oldest and most common material used for this is copper wire. Early copper lines faced a severe physical limitation. Parallel wires act as fine antennas. Running them next to each other causes them to absorb electromagnetic interference from the environment and from adjacent lines, creating massive signal distortion known as crosstalk. The geometric solution to this is the twisted pair. By winding 2 wires together into a double helix and sending the signal as a differential voltage, incoming noise affects both wires equally. The opposing twists force the noise vectors to cancel each other out mathematically to 0. Looking at our matrix, twisted pair is highly cost-effective and easy to deploy for local area networks. However, the electrical signal attenuates rapidly, restricting it to very short distances. Overcoming bandwidth and distance limits of twisted pair requires a structural upgrade to the copper itself. Coaxial cable abandons twisting entirely. Instead, it features a stiff copper core surrounded by an insulating layer, which is then encased by a closely woven braided outer conductor and a thick plastic sheath. That braided cylinder acts as a continuous Faraday cage. It physically blocks external electromagnetic noise from entering and prevents the internal high-frequency signal from leaking out. Coax achieves significantly higher bandwidth and spans much longer distances than twisted pair, making it the backbone of cable TV networks. The trade-off is higher cost and a much bulkier physical footprint. Copper transmission relies strictly on geometric shielding. Engineers must use helices and continuous cylinders to protect electrical pulses from their physical environment. To completely bypass the physical limitations of electrical transmission, network architecture moves away from moving electrons along metal wire and instead fires photons through glass. An optical fiber relies on 3 specific components: a central glass core only microns thick, a surrounding glass cladding with a lower index of refraction, and a protective outer jacket. This medium works due to a principle called total internal reflection. When light enters the core at or above a specific critical angle, the differing refractive indices of the core and the cladding force the light to bounce perfectly inward, trapping it. The propagation path depends on the core's diameter. Single-mode fiber uses an incredibly narrow core to send a direct laser path over vast distances. Multi-mode fiber uses a wider core, allowing multiple LED light pulses to bounce along the walls for shorter intra-building links. Plotting this on our matrix, fiber optics dominates the performance metrics. It supports massive throughput in the terabits per second range, spans 50 kilometers without repeaters, and carries no electrical current, making it immune to electromagnetic noise. The penalties for this performance are cost and flexibility. Optical interfaces are expensive. The glass core can physically shatter if bent too sharply, and communication requires 2 separate fibers for bidirectional traffic. Fiber optic networks trade physical flexibility and hardware costs for absolute environmental isolation and maximum throughput. The alternative to building a physically closed environment is to abandon cables entirely and broadcast raw data through free space. With unguided media, the engineering challenge moves away from physical deployment. The absolute focus becomes managing and regulating the electromagnetic spectrum. The most common unguided medium is radio. Radio waves are defined by their omnidirectional propagation. They broadcast outwards in all directions simultaneously. Because radio waves operate at relatively low frequencies, they can easily pass through solid obstacles like building walls. This allows devices to maintain a network connection while in motion. The trade-off is intense interference, rapid distance drop-off, and no inherent physical security. Moving up the spectrum, microwaves operate at much higher frequencies. This allows them to carry significantly more data in a highly concentrated unidirectional beam. Because they do not bend or penetrate obstacles well, microwaves require strict line-of-sight alignment. They are highly vulnerable to physical interruption and weather phenomena, which can scatter the waves and cause multipath fading. Despite these vulnerabilities, erecting 2 microwave towers is far cheaper than trenching 50 kilometers of terrestrial fiber over a mountain range, making them vital for cellular tower backhaul. Infrared communication sits even higher on the spectrum. Its defining physical limitation is a total inability to pass through solid objects. In network design, that lack of penetration is a targeted advantage. It provides absolute spatial security within a single room and naturally prevents cross-interference between adjacent offices. When terrestrial geography is too hostile for cables or towers, we use satellite communication. Satellites are essentially massive microwave repeaters placed in orbit. They operate on a bent pipe mechanism. A ground station sends a single, concentrated uplink transmission to the satellite, which amplifies the signal and rebroadcasts it into a massive terrestrial downlink footprint. For satellites, the transmission cost is completely independent of the distance between the endpoints on the ground. However, because the signal must travel to space and back, it suffers from severe propagation delay and offers zero inherent privacy. Unguided media deliberately sacrifices the perfection of a closed copper or glass environment in order to provide edge mobility and rapid deployment. This complete engineering optimization matrix brings all 7 mediums together across our 5 physical variables. Looking at the data, fiber optics mathematically dominates the alternatives, providing the highest possible ceilings for speed, distance, and noise resistance. But optimal engineering is about context. Twisted pair remains the superior choice for local cost efficiency, while wireless media is the only option when endpoint mobility is required. Before we finish, let's lock in the core principles with 3 quick revision notes. First, guided media explicitly confine signals to protect them. Unguided media broadcasts them through free space. Second, copper relies on geometric shielding, like twists and braids, to survive interference. Fiber relies on the material physics of optical refraction. Third, wireless network design shifts the engineering burden from laying physical infrastructure to managing spectrum interference and line-of-sight logistics. Let's test your understanding of Layer 1 physics. Consider this. Why does twisted pair wiring become far less effective at mitigating crosstalk as transmission frequencies enter the gigabit range? Second, if a submarine fiber optic cable is physically severed, the data loss is immediate. Why can a satellite link maintain a constant, albeit delayed, connection across that exact same ocean geography? Finally, why are infrared communications completely exempt from government spectrum licensing, unlike radio and microwaves? Understanding these physical constraints is the first step in designing a network that survives the real world. By balancing these variables, architects ensure the digital world stays connected.